So last class we discussed up to like paired data, right? And I told you guys that it should always like maintain a consistent order, right? If you recall that a paired data should always have a consistent order, right? So in this example, like the reading and writing data is there. So they have found the difference by subtracting reading minus writing. Okay, so it's like reading minus writing, and that's the difference. And this should always maintain a consistent order, right? So when we try to analyze a paired data, we must make sure that the order is consistent, right? So now let's talk about the parameter and point estimate. So what's the parameter of interest here? Here it's the average difference between the reading and writing score of all high school students. Okay, and what's the point estimate? Is the average difference between the reading and the writing scores of sampled high school students. So when I talk about point estimate, whenever I talk about point estimate, it's always sampled. Okay, and parameter of interest, it's like all high school, so it's it's highlighted. So point estimate, whenever I say like it's a point estimate, you should know that it's coming from the sample data. Okay, it's not the population. So this is not population data. Okay, whenever I'm talking about sample, okay, not population, right? So let's now set up the hypothesis. So if in fact there was no difference between the scores on the reading and writing exams, what would you expect the average difference to be? If there is no, like we are saying that there is no difference, right? So it would be 0, right? The reading and writing. So the null is like it should be 0. So what are the hypotheses for testing if there is a difference between the average reading and writing scores? So if we want to, so the null, you guys are agreeing that if we are saying that there is no difference between the scores, the null is 0, right? There shouldn't be any difference. So the null should be that the difference coefficient is 0, right? And if there is a difference, then the alternate we always write is as HA, and then we say the difference is not equals to 0. So the difference can be either positive or it can be negative, right? If it is greater, then it's positive, like if the reading score is greater than the writing, and if the reading score is lower than the writing, then it's a negative difference. So nothing new here, right? So the analysis is no different than what we have done before, and we have data from one sample, which is the difference, and we are testing to see if the average difference is different from 0. So it's similar to what we have done in the hypothesis testing for the chapter 1, right, in the previous case, right? And so how do we decide that we want to reject or we want to accept the null hypothesis? If you recall from chapter 4, I said that we decide depending on the p-value, right? So if the p-value is small, like it's less than 0.05, then we usually reject the null, right? So if, let's say, if I draw a normal distribution and let's say the p-value is here 0.05, if it's a smaller value, like we get the p-value as, like, let's say 0.03 for example from our calculation, right? Then we reject we reject the null. So then in that case we reject the null, right? So reject null hypothesis. So here if you look at this example, the observed average difference between the two scores is 0.545 between reading and writing. They have also given us the standard deviation, which is 8.88. Do this data provide convincing evidence of a difference between the average score on the two exams? So use alpha equals to 0.05, right? So we have, okay, so I'll do it in the blackboard for this. So they have given us the difference, which is 0.545, right? And standard deviation is 8.88, right? And they are saying to test the significance level is 0.05. So over here, if you recall the formula that we did, so we have to take the difference minus the null, and divided by the standard error over the number of like observations, right? So let me show you guys, because this is a t statistic, okay? It's not a normal. So let's look at the formula one more time. Okay. So this is the formula for testing the hypothesis, okay? Point estimate minus the null value, which is, what's the null value? That there is no difference, right? So the null value will be always 0, right? So null value would always be 0. If the null is, there is no difference. And the degree of freedom, you always have to consider the degree of freedom for t-stat. Okay, so the degree of freedom here, if n is 200, in this case n is 200, so degree of freedom is 199, right? So if you see the degree of freedom 99. So we have actually used the formula in slide 64, which is the difference minus the null, right? And then standard error over root n, right? So this is the formula. Is this clear to you guys? How to use the formula? Like if you have any questions, please let me know, because this is important to understand. Let's see, where is it? Yes. This is important to understand to test the hypothesis test. Okay, this is the formula in slide, it's in slide 58, not 64. So slide 58. Right. So we got the p-value to be 0.3854. Since the p-value is greater than 0.05, we fail to reject the null. Okay, you should write the entire thing. Okay, when you are writing, you should say that as the p-value is greater than 0.05, like we calculated the p-value, like once we actually know the value and also the degree of freedom, right, you can go to the t-stat table. So let me show the t-stat table to you guys. Okay, just a recap. So you have to choose the degree of freedom from this value, and it was like 0.87, right? So 0.87, it's not here, but let's so I can actually show you guys uh, a, like a t table. Okay, so I will give some examples in class, like later. So we will see how to actually look at the t table. So setting the hypothesis should be straightforward, okay? And this video is also being webcasted because I want to make a consistent. So entire chapter 5 is webcasted there. So those who have come late, like 10-15 minutes, you will be able to see the like what I have taught in class, right? So we reject them now. So is it clear to everyone? Any questions? Victory, you had a question that you posted on the link, that the main difference is the critical value of the the t distribution and the normal distribution. Yeah, that is the main difference. Apart from that, it's also about the shape of the curve, right? Because a normal distribution, if I draw this is let's assume this is a normal, then the t would be something slightly fatter tails. So their tails are fatter. Okay, so that is also one of the like difference between a normal and a t. Okay, I'm just assuming this to be normal. Okay, but in this example, actually, they are treating it as a t distribution. Okay, so suppose we were to construct a 95% confidence interval for the average difference between the reading and writing scores. Would you expect this interval to include 0? Okay. Yes, because the difference also includes 0. If there is no difference, then within this confidence interval there should be 0. All right, and using the example from the previous case, okay, if we construct a confidence interval, so what is the confidence interval for a t distribution? It's the average difference plus minus the t distribution critical value times the standard error over root n. Okay, this is the confidence interval formula for a t distribution. So what's the difference between reading and writing? Is negative 0.545. What does the negative sign say? That the reading score is lower than the writing score, right? And what is the t value? Oh, there is a typo here, right? This is a typo. Okay, this should be 1.97. Okay, times the standard error over root n. Okay, you can go home and check. Yeah.
Isn't standard error equal to standard deviation divided by root n?
Standard error, yes. Standard error. So let's go back there. Okay, it's the standard deviation over root n. Yeah, you're right. So, okay, so let's see. Yeah, I should have written standard deviation. That's a good point. Okay, this is standard deviation. Standard deviation, and this is standard deviation by root n, right? And this whole thing is actually standard error, right? So it should be standard deviation. Thanks to Brandon for pointing it out. So you guys should always read the slides, and if you find any mistakes, or if I'm doing some mistakes, please point out. Okay. So now we will actually talk. So is this clear to everyone how to construct the confidence interval? you guys should have a formula sheet in the midterm, so you will be able to use the formula sheet. So make sure you write down all the formulas, like formulas for confidence interval, formulas for constructing the hypothesis test, right? It's the difference minus the null divided by standard deviation over root n, or divided by the standard error, right? In fact, this is a shortcut, but so that you guys don't make any mistakes, for any t distribution, it's always difference minus 0 over standard error. Okay? And what is standard error? Standard error is nothing but standard deviation over root n. Right? Let me write it in somewhere else here. Standard deviation over root n. Okay, so this is like a shortcut, and null, usually, like I have said, like conventionally we use the null as 0, like there is no difference. Always you write it in that manner. Right? So now we will actually, look at like comparing the means with Anova. Okay. So if you see, this is the Wolf River in Tennessee, and it flows past an abandoned site once used by the pesticide industry for dumping waste. Okay, so the waste includes like chlorodyne, aldrin, and daldrin, both insecticides. So these highly like toxic organic compounds can cause like various cancers and birth defects. And the standard method to test whether these substances are present in a river is to take samples at 6/10 depths. Okay, so that's how it is measured, like or tested, that whether the substances are present or not, right? But since these compounds are denser than water and their molecules, let me just reduce it. Okay, and their molecules tend to stick to particles of sediment, they are more likely to be found in higher concentrations near the bottom. So this pesticides, if it is dense, it doesn't float. It actually, it goes to the bottom of the surface, right? Because it's heavier than water. So let's see like how they have measured. Okay, so aldrin concentration, like they have found the aldrin concentration is nanograms per liter. Okay, the measurement at 3 levels of depth. So they look at like bottom depth, okay, at mid path, and also at the surface. Okay, generally we would expect the aldrin concentration to be higher at the bottom depth, right? Because these are denser substances. So if they're dense, the higher concentration would be at the bottom, right? So they have actually, like based on the graph, if we see that the concentration level is slightly higher at the bottom compared with, let's say, the middle, mid path, and also the surface, right? So now actually what they did, they have actually constructed the mean. So they have collected the sample from 3 different paths. One is the surface, one is the mid path, another one is the bottom surface, right? So if you see, the bottom surface mean value is higher, and it is expected because they are dense and they tend to be found at the bottom of the river. The surface mean is actually slightly lower than the bottom, and the mid path is actually in between those 3, right? Is it clear to everyone? Like, what is aldrin? Aldrin is a toxic substance, okay, and these are causing like cancer in like among people. So they collected the sample from three different layers, and they found that the bottom layer has a higher mean. So now, is there a difference between the mean aldrin concentrations among the three levels? Definitely, if you are looking at the data, there is a difference. So how do we actually test this? So to compare means of three groups, we use a new test called Anova and a new statistic called the F statistic. Okay, so F test statistic is always used when we are actually dealing with multiple groups. All right. So when we are comparing only like null and alternative, it's just a single difference, right? Now the difference is between three groups, right? Lower level, mid path, and the surface. If the difference is between 10 groups, let's say I want to see the class performance of my, let's say the economics department decide to look at the class performance in different sections, right? We have 16 sections in the like micro and macro, like 8 each. So in that test, they have to use a F stat to see, compare the mean, right? So ANOVA is used to assess whether the mean of the outcome variable is different for different levels. So it's if it is different for different levels, okay, this is the key point, right? So, and what should be the null now? What should be the null? By convention, we assume that there is no difference. So in that case, all the means should be same, right? Mean 1, mu 2, mu k. Mu 1 could be the mean for the surface, mu 2 could be the mean for the mid path, mu k could be the mean for the bottom surface, right? So when we are saying that all 16 sections in the economics department student would perform similarly, that means the mean GPA of each class should be same, right? So mean GPA, so I'm just using the economics example, mean GPA of section 1 should be equal to mean GPA of section 2, mean GPA of section 3, mean GPA of section 4, and so on and so forth until mean GPA of section 16. Okay, so when do we construct an F stat? When we are trying to analyze between different groups, multiple groups, not just only one difference, right? And what would be the alternate? Alternate would be at least one mean is different from others. Even if only one mean is different, that means the F stat would say that no, not all the means are same. Okay, so this type of actually like in the policy level, let's say because since I'm researching on health economics, at the policy level, let's say like if they have given certain kind of health policy, let's say Obamacare, right? So after implementing Obamacare, they want to see if the number of patients that are getting admitted has dropped significantly or not, and then they say that okay, it should be about the same in Michigan, same in Ohio, same in Indiana and Wisconsin. So that's the hypothesis, right? The null hypothesis. If it is same in all states, then maybe it's a good policy, right? But even if one of the state is different, then it is a cause for concern, right? In reality, do you think all the states are performing same in real life? It's hard because there are different kind of factors that can influence it, right? Some states are because of geographical location. If you are, let's say you are in Arizona, right, a dry area, health condition, because of dry area, like not maybe a lot of like water bodies, and that might cause some kind of problem. So those are external factors that can cause problems. So once we control for those factors, and if still there is a difference, then the f stat will say, if we, like in those kind of example, f stat would say that even after controlling for the difference there is a difference, then the policy should be considered to be like changed or something like that, right? Is that clear to everyone? So how do you set the null for f stat, or this is also sometimes called the Anova, right? So is it clear to everyone? When the mean are same, then there is no case for concern. Like if our department finds that the class performance of my section and the other teachers are same, okay, that's the null. And why do you use f stat? Why? Multiple groups, right? More than one. So when there is more than one group, you're comparing among like different groups, you use a f stat, right? So is it clear? You can watch the video again, and if you don't get it this time, so this would be also put onto the channel. All right. So conditions. So let's look at the conditions. It's similar that it should be independent, should be randomly sampled and less than 10% of the population, right? It's similar to the chapter 4 assumptions, so the CLT conditions, similar, right? And no pairing, carefully consider whether the data may be independent. If there is pairing, then they are dependent, right? Like if someone is good in English, their writing score would be higher. Not only their writing score, their reading score would be higher as well as their speaking score, right? So they are paired in that sense, right? So if they are paired, then we cannot construct the hypothesis as such. All right. So the observation within each group should be nearly normal. We always assume normal assumptions. Okay, so if it is not normal, then again it's a problem for constructing the test, right? So how do you check for normality? So these are the tests. Like we check skewness. We don't want too much skewness, right? Normality assumptions, the skewness should be as less as possible, or we can do a QQ test. You can use it in Stata, okay, this QQ test, right? That will tell us if it is normal or not by looking at the QQ. Is like the it's the like quartile basis, okay, QQ. And the variability across the groups should be about equal, and especially important when sample sizes differ between groups. Okay, so we also want the variability to be about equal. Right? So if we are trying to construct the Anova, so first on the numerator is the variability between groups. So variability between different sections, right? And in the denominator is the variability within groups. So it would be the variability within the students. Okay, like in my section, we would expect that not everyone to get the same type of scores, right? Do you think all of you guys will get the same score in the midterm exam? No, right? Because some students will put more effort, some students will put less effort, some students would be smarter, like they might not need to study that much, some students need to work harder, and so on and so forth. So there is not only variability between groups, like variability between different sections, like let's say my section is, I believe it's section, let's assume it's section 1, all right, my section, right? There are 16 sections in the department, so section 2 ... it continues till section 16. Okay, so there could be difference between each group, Not only that, within each section, so in my section I have a lot of students, right? Like I have Tom, maybe I have John, or Michael. Okay, even within my section there could be variability, right? Like Tom might like get a different score than John or Michael. So when F test is not only variability between the groups but variability within the group. So within my section there is a variability, right? So that's how we construct the F stat. So large test statistics lead to small p-values, similar to the z distribution, right? When the z test statistic was high, the p-value was lower. So F stat also similar in nature. If the p-value is small, H naught or null is rejected. So same. If p-value is small, H naught is rejected, and we conclude that the population means are not equal. Okay. Another way you guys can look at it is it's trying to find the joint significance kind of thing. Okay. So actually, let me show you guys something, right? Let me just create a new slide. Okay, so I had a model in my like I was trying to find the total health expenditure of a country. I used the World Bank dataset of 120 countries. Whether the total health expenditure depends on smoking, it's like beta naught smoking plus beta 1, let's say drinking, plus beta 3, like I had smoking, drinking, whether on education level. Okay, and so what do you think if a person is smoking? If you look at this equation, let me just write education like this. Alright. So in general, what do you guys expect? If a person is smoking, like in each country, okay, I used like a panel data. We will talk about panel data later. Let's just assume if a person is smoking, then the total health expenditure of that country should go up, right? That's your hypothesis, that if a person is smoking more, then the total health expenditure of the country would go up. Okay, that's a bad thing. We don't want the health expenditure of a country to go up that rapidly. If a person is drinking, or in a country, the more people are drinking, that means their health will deteriorate. They have to go to the doctor frequently, and again their health expenditure is going to go up, right? This is our hypothesis. So how did I set up my null hypothesis? What is the convention of setting up? And now actually I'm looking at 3 different groups. If you are educated, higher level of education, if you are highly educated, your health expenditure may go down or may go up as well. How will it go down? Because if you are educated, you will eat healthy food, you would avoid junk food, and that way maybe you will go less to the doctor, and if you go less to the doctor, the health expenditure should go down, right? This is one way of seeing things. So I said the hypothesis in such manner is that, so the null hypothesis is, I just assumed that there is no difference between, like I assume beta 0, right, equals to beta 1 equals to beta 3, and they are equals to 0. Okay, so I said these coefficients would be 0. This would not make any difference to total health expenditure. And if you look at this is like an F test. Agreed? It's like an F test because I am assuming they are 0. This coefficient of the variables, like these values will not impact the health expenditure. This is the null. What is the alternative? Alternative is at least one of them would be non-zero. So at least one would be not 0, like one of the values. So is it clear how to construct a hypothesis? And here I'm comparing about like I just assume 3 different groups: smoking, drinking, and like educated people. So EDUC is like if they are highly educated. Is it clear to everyone? Right? So hypothesis null is there is no difference. All the means are same, or maybe all of them are equals to 0. And alternative is they are not. At least one of them is not equal to the other. Right? Did I erase something? Okay. So at least one mean is different. Okay. It doesn't have to be all the means have to be different, no, or all the means is same. So at least one is different. Alright. In my case, all the values were, I assume all the values to be 0. Beta 1 equals to beta 2 equals to beta 3 equals to 0. That was my null. Alright. So that's how you set it up. So this is again coming back from that example of the pollutants in the Wolf River in Tennessee, the aldrin particle which is cancerous. So if we look between the 3 groups, let's use a different color. If we look like this is bottom group, this is the mid path, and this is the surface, right? You can see that their means are different, right? Means of each of the groups are different. Mean of the bottom was 6 point something, right? Mean of mid path was 5.2 or something like that, and surface was 4 point something, right? If you go, so mean, there is variability between groups. Now let's look at each of the observation within group. So within each individual, there is also difference, right? Are they same? If they are the same, all the dots should be at the same point. Are the dots same in within each group? Like within each group? No. Like, are you guys all the same? Are you guys all have the same GPA in this class or maybe in other class? No, because there will be difference, right? So there is variability not between only groups but also within groups. Even within groups, these dots and these dots are not same, they are different, right? So there is variability, so we can construct an F test. Okay. And in textbooks you will see that it's the variability between groups and within groups. Sometimes it is like MSG between groups and MSE. So in order to be able to reject null, we need a small p-value. So it's always we need a small p-value, then we can reject the null. Okay. So in my case, when I said beta 0 equals to beta 1 equals to beta 2, when I gave you guys the health example, I found a p-value was less than 0.05. What does it say? Should I reject my null? We should reject our null, right? If my p, I got the f state value, like I used stata, and I found the p value was less than 0.05. So if I reject my null, what does it mean? That means at least one of them is not equal to 0, right? At least one of them is not equal to 0. In fact, I found all 3 of them were not equal to 0. They were for health I got like 0.3 maybe, and the smoking variable I got 0.3, drinking 0.2, I found a lower value for the drinking. And for education, in fact, I found a positive coefficient, although I was expecting a negative, but I found a positive coefficient. Okay, it's like education. So in order to obtain a large F stat, variability between sample means need to be greater than the variability within sample means. So if you look at the F stat, we want the variability between groups to be higher than the variability within group. In this case, the variability of the bottom, middle and surface, like these three groups, the between groups are higher than the variability within groups. It is clear from the data, right? If you see, so variability of this group and this group and this group. So I am trying to find the variability between three groups. So I can see that the mean of this group would be centered around here, mean is centered around here, for mean maybe it's centered around here. So there is a huge variation between group. Within group the variation is not much, right? Not much. But you can argue that the bottom group has like a little bit more variability. Okay, but the between groups is like different section, like section A, section B, section C. Like I said that we have 16 sections in our department, right? If the variability is greater and the variability in my class is like smaller, like if I teach well and if all my students participate in class, most of them will get good grades. So variability between the like within the group is smaller and variability between groups would be larger. Okay, so then it's a case that the department should try to implement, like maybe they should try to teach like give like webcast lessons or something like that to reduce the variability within groups. Okay, also it will help reduce between groups. Okay, so here the sum of square like within group, you will see that this is the sum of square, this is the mean square, and so where here MSG is the k minus 1, where k is the number of groups. Okay, so they also have a degree of freedom. Not only the t-stat have a degree of freedom, even when we are going to do an f-stat, they will also have a degree of freedom. So MSG is the sum of squares in the number of groups, and MSG is the sum of square residuals, or sometimes it is called the mean square error. Alright, and what is the formula for f-stat? Is MSG over MSE. This also should go to your formula sheet. So MSG is the sum of squares between the groups, and this is the sum of squares of residuals. So if we go back, yeah. So this captures the variability between the groups, and this captures the variability within the groups. All right. So if the degree of, so if we look at this example, how many groups are there in the between groups? How many groups are there from the example we used? There was a bottom surface, mid path, and there was the surface, right? So how many groups are here? 3 groups, right? So between groups, what would be the degree of freedom? It's k minus 1. So 3 minus 1, so it should be 2. Right? Can you follow like the class? So we have 3 groups, between groups, and within group. So within each group, they have n, the sample size as 30, and their formula is n minus k. So total sample size is 30, right? And what is the number of groups? K is the number of groups, so minus 3. So n minus k, it will give us 27. Okay. So we got the degree of freedom for MSE as well. And what is the mean square error? Mean square error is calculated as sum of squares divided by the degree of freedom. So this is the sum of squares So sum of squares is this and this. You divide it by the degree of freedom, you got the mean square error. And the ratio of this mean square error would give you the f value. And we would get the p value. Okay. There is a distribution table for f value as well. So first thing, we need to find the mean square error of the group. We need to find the mean square error of the error, which is the residuals, and the ratio of these two would give us the f value. So how do you calculate the mean square of the group? It's sum of square of the group divided by the degree of freedom of the group of G. How do you calculate MSE? Sum of squares of the errors divided the degree of freedoms of error. Right? Is it clear how? And then the ratio of MSG over MSE will give you the f value. And let's look at the f table. So when we are calculating the f table, I will also give you guys the f table in in fact I am going to show you guys right now. So I will show you f table. I will show you the t table and as well as the normal table, and we will see. So how did they calculate the p value from there? Okay. So if p value is small, we reject. We already know this. So you guys can read the last 3 slides yourself. These are the same thing that we have talked. Let me just discuss something. Okay, in a Z distribution, what's the degree of freedom? Or do they have any degree of freedom when you are trying to calculate? Do you get any degree of freedom? No, right? In a Z distribution, we don't. Okay, we don't get like a degree of freedom here, right? Not needed. In a T distribution, you get only 1 degree of freedom, right? And I said if the degree of freedom increases, then what happens to the T distribution? Like, how does it behave? What's the behavior of T distribution as the degree of freedom increases? It behaves like more normal. Yeah, so if degree of freedom is larger, so if let's say n is like 90, it's a very big number. What's the degree of freedom for T distribution if n is 90? What's the formula? N minus 1, right? For T distribution, so it would be 89. And it will behave like a normal. The critical values of T would be similar like normal, as Victoria asked in one of the like YouTube videos, right? What about F? F distribution. How many degree of freedom do you have? we have two types of degree of freedom. One is the between group, another is within group, right? So when you see an F distribution, they have between group and within group. So we have to look at the two types of degree of freedom to find the associated value, okay, the critical value. So I am going to show you guys some things from the, let's see. Okay. So I'm going to switch over to that PC.